Welcome to Theory of Computation. This is lecture number 38. As you recall, we have been studying space complexity, and before that we were studying time complexity. When we were studying time complexity, we defined two very important classes. One was P and the other was NP. That was in order to measure what happens to time when we go from determinism to non-determinism. Well, now we're doing a different kind of analysis. Now we are looking at problems from a space point of view. So our motivation is completely different. Typically in algorithms course, you learn how to design efficient algorithms, and most of the time when you come up with a fast algorithm, that is usually considered to be a good algorithm. An algorithm which runs fast is a good algorithm. However, now our motivation is different. Now we want to look at space-efficient algorithms. We want to characterize problems according to their space complexity. We looked at several algorithms or Turing machines, and we looked at how much time and space they take. And then what we did was we tried to come up with better algorithms which solve the same problem but require less space. In this case, time was not a consideration for us. We've also looked at something called the reachability problem in graphs, and we realized that our favorite algorithms, depth first search and breadth first search, although they're time efficient, they were not space efficient. There was this beautiful idea of Savage, which gave a space-efficient, extremely space-efficient algorithm to solve the reachability problem. We were able to solve it in space order log squared of n. And then we realized that this idea can be used to prove an extremely interesting question in complexity theory, and an extremely important theorem called Savage's theorem. Savage's theorem solves the P versus NP analog for space complexity. See, we realized that when we were studying time complexity, the P versus NP question is an extremely deep and important unsolved question. So we defined these two classes called P space and NP space, and we asked the same question, whether these two classes are the same or whether they are different. Well, Savage's theorem solved this problem for us. Savage's theorem roughly says that if you have a non-deterministic Turing machine that runs in space S of n, then you can find a deterministic Turing machine that solves the same problem or accepts the same language, and it would run in space at most order S squared of n. And this was amazing because it showed that at a quadratic slope, you can get rid of non-determinism. This means that all the problems that can be solved in polynomial space, non-deterministic polynomial space, can also be solved in deterministic polynomial space, because as at a quadratic blow-up, you can get rid of non-determinism. Therefore, the analog of the P versus NP question, the P space versus NP space question, is solved, and both of these classes are one and the same. Well, if we look at a study of time complexity, when we define this class NP, then after that we ask the question if there are any complete problems for NP. So we can play the same game with space complexity. We can say that we have defined this class P space, and does P space contain any complete problems? And this would lead us to a theory of P space complete problems. Do we have any understanding of P space complete problems? Can we identify many interesting problems which are P space complete? Is there some characteristic these problems have which make them P space complete? If you recall, NP complete problems seem to have this one very interesting theme in them, that they were in some sense existential questions. Well, is there something similar that we can say about P space complete problems? Can we find out a big repertoire of p-space complete problems and then look at them and see what kind of problems do we get. These are the kind of questions that we're going to explore in today's lecture. The outline of today's lecture is going to be, first we will review some very basic questions, basic relationships between space and time complexity. After that, we would look at the class p-space. Then we will define and understand the notion of p-space completeness. And then in the end of the lecture, what we will do is we'll look at one particular problem which is going to turn out to be p-space complete. This problem is called QBF. So let us begin today's lecture. QBF is a generalization of the satisfiability question. It's a more complicated problem than satisfiability. Satisfiability turns out to be a special case of this problem called QBF. But QBF is an amazing problem because what it is it's going to turn out to be p-space complete. As we'll see, when a problem is p-space complete, that essentially means that it's even harder than an NP complete problem. It's even more unlikely for this problem to be solvable in polynomial time than it is for a problem which is NP complete to be solvable in polynomial time. Well, let's start with today's lecture. Let's review some relationships between space and time, determinism and non-determinism. Let's look at the first relationship here. It says that d time of t of n is contained in n time of t of n. What does this mean? D time of t of n is contained in n time of t of n. Well, this is a simple set containment or containment between classes. And if you read this thing, what it says that if a problem can be solved in deterministic time t of n, then it can also be solved in a non-deterministic time in time t of n. So, if you go from determinism to non-determinism, there is no time penalty. How would you prove such a thing? Well, the proof of it is trivial. Almost nothing is to be done. The only thing that we need to observe is that every deterministic algorithm or every deterministic Turing machine is also a non-deterministic Turing machine. So that was very easy. That was our first relationship. Let's look at the second one. The second one says that d space of S of n is contained in n space of S of n. How would we prove such a thing? Well, the first thing we have to do is read this thing properly. This statement is saying that if we have a language which can be solved in deterministic space S of n, then it can also be solved in non-deterministic space S of n. Well, the proof is once again almost trivial. Every deterministic Turing machine is also a non-deterministic Turing machine. Thus, if you have a deterministic Turing machine which runs in space S of n, the same Turing machine, you can consider it as a non-deterministic Turing machine that runs in space S of n. Let's look at the next one. The last relationship says that time S of n is contained in d space S of n. How do we prove such a thing? Suppose that you have a Turing machine, deterministic or a non-deterministic Turing machine, that runs in time S of n. Then why is it that it cannot use more space than S of n? Well, that's very simple, because the Turing machine can at most use one more tape cell every time it takes a step. So the time taken by the Turing machine is an upper bound on the space taken by Turing machine. All these three relationships between space and time, determinism and non-determinism, are absolutely trivial. In the sense, all you have to do is read these statements and look at them and realize that whatever machine you're given, you don't need to do anything to it in order to prove that it's contained, that the language is contained in the other class. So these are absolutely simple statements. Now let's look at some other relationships where we have to do a little more work. And these are going to be relationships between space and time, determinism and non-determinism. Let's start. Here are the non-trivial ones. The first one says that non-deterministic time t of n is contained in deterministic time 2 to the order t of n. So, this statement says that you can get rid of non-determinism at an exponential cost in time. So, if you have a Turing machine that runs in time t of n and it's a non-deterministic one, you can make an equivalent deterministic Turing machine that takes time order 2 to the order t of n. So, if you are willing to pay an exponential penalty in time, you can get rid of non-determinism. The proof of this is once again very simple, but it's harder than the previous relationships that we saw. Suppose you have a non-deterministic Turing machine that takes time t of n. What you want to do is make a deterministic Turing machine that takes time 2 to the order t of n. Well, a non-deterministic computation is a tree, it's a computation tree, whereas a deterministic computation is simply a linear thing. Now, what you can do is you can make a deterministic Turing machine that goes through the non-deterministic computation painfully by going around this whole tree. And what you can do is you can easily prove that this tree will have exponentially many nodes. And therefore, the upper bound on the time taken by the deterministic Turing machine would be exponential in the original time. So that's the proof of this, that you can get rid of non-determinism at an exponential cost in time. Let's look at the next relationship. This relationship says that non-deterministic space S of n is contained in deterministic space S squared of n. And of course here we have a condition that S of n should be greater than or equal to log n. And this is Savage's theorem. This relationship is by no means trivial. If I were to write down this statement for you and say, prove it, well, you would have to be very smart, very creative to be able to come up with the proof that Savage came up with. But this is Savage's theorem, and it says that what you can do is get rid of non-determinism at a quadratic penalty in space. So if you're willing to spend quadratic amount of space, then you can get rid of non-determinism. For every non-deterministic Turing machine that runs in space S of n, you can find an equivalent deterministic Turing machine that runs in space S squared of n. Let's look at the last relationship. The last relationship says that deterministic space S of n is contained in deterministic time 2 to the order S of n. Well, what does this relationship say? This relationship is trying to relate time and space. So what we have is we have a Turing machine that runs in space S of n. And what we want to know is how long will it take for it to finish its computation if we are guaranteed that it would not use more than space S of n. Well, to prove this thing, all you have to do is some counting. What you can do is you can prove that if a Turing machine uses space S of n, then the number of configurations it can have is 2 to the order S of n. Therefore, if that Turing machine takes more than 2 to the order S of n time, that means that Turing machine is not going to halt because one of the configuration must have repeated. This means that if you're guaranteed that your Turing machine halts on all inputs, then it must finish its computation in time less than 2 to the order S of n. In this case also, it doesn't really matter if your initial Turing machine was taking deterministic space S of n or non-deterministic space S of n. So these are very simple relationships between space and time, non-determinism and determinism that you should learn, and you should not try to memorize them, but understand why these relationships are true. And you should be able, when one of them is given to you, you should be able to look at it and say that, oh, I know how to prove this also. One of the proofs there is extremely ingenious, that is Savage's theorem. The other two are counting, and the three relationships that we discussed earlier were all extremely trivial. There is essentially nothing to be proved, just the statement has to be read properly. Let's continue. Now let us define our favorite space complexity classes. Well, let's look at what were our favorite time complexity classes. So we go back and look at our study of time complexity and use similar ideas to study space complexity. So what were our favorite time complexity classes? Well, one was P, which was polynomial time. The other was NP, which was non-deterministic polynomial time. And the third one that I have written here is exponential time, which means that if you can solve a problem in time 2 to the order n to the k for some fixed k, then we say that that problem is in exponential time. Now let's define non-deterministic complexity classes. Well, the analog of P is going to be P space, and the analog of NP is going to be NP space. So P space is the set of all problems that you can solve in polynomial space. Similarly, NP is the set of all problems that you can solve in non-deterministic polynomial space. Let's see what we can say about these things. If we think about all these complexity classes, we will find that we have the following relationship. So this is a simple linear containment relationship that I'm going to read, and this relationship is that P is contained in NP, which is contained in P space, which is equal to NP space, and NP space is contained in exponential time. Well, let's go through one by one. Why do we know these containments hold? Well, let's look at the first one. Why is it that P is contained in NP? One line proof. We just say that every deterministic polynomial time algorithm is also a non-deterministic polynomial time algorithm. So that's the proof of the first containment. The second containment says that NP is contained in P space. Well, before discussing this containment, let's look at the third one and see why that is true, and then I will discuss this particular containment. The third relationship there is not actually a containment, it's equality. It says that P space is equal to NP space. Well, first thing is, why is it that P space is contained in NP space? That's once again trivial. Every deterministic polynomial space algorithm or polynomial space Turing machine is also a non-deterministic polynomial space Turing machine. But why is it that the reverse containment also holds? Why is it that NP space is contained in P space? Well, that's Savage's theorem, because Savage's theorem says that you can get rid of non-determinism at a quadratic penalty in space. Since the square of a polynomial is a polynomial, therefore NP space is contained in P space, and therefore these two classes are equal. This is the celebrated Savage's theorem. Now let's go back and look at why the containment that we saw before is true. That containment was that NP is contained in P space. Well, since P space is equal to NP space, therefore I will argue that NP is contained in NP space. That's almost trivial. If you have a non-deterministic algorithm that runs in polynomial time, then it cannot be using more than polynomial space, because at every step it can only use one new tape cell. And that statement is trivial, that NP is contained in NP space. But since NP space is equal to P space, therefore NP is also contained in P space. The last relationship on this slide says that NP space is contained in X time. Well, if you go back and look at the facts that we saw, we said that if a computation can be performed in space S of n, then it the exponential of the space is an upper bound on the time taken by the algorithm, and it's just that relationship that is being used here. Therefore, now we know that NP space is contained in exponential time. So we have a chain of containments here with one equality. So far, complexity theorists have only been able to prove that P is not equal to X time. So we know that the class P and the class X time are two different classes. In other words, there is one problem. There's one problem that you can solve in exponential time. However, you cannot solve it in polynomial time. And here, exponential means 2 to the order polynomial. So there is a problem that you can solve in 2 to the order polynomial time, but you cannot solve it in polynomial time. This is known to complexity theorists. They know that these class P and X are two separate classes, two distinct classes. Therefore, from there, it follows that all the containments that I have given to you in this slide that are written there, one of them must be non-trivial. At least because P is contained in NP, which is contained in P space, which is equal to NP space, which is contained in X time. But P is not equal to X time, therefore one of these containments must be non-trivial. So one of these containment must be strict. However, we do not know which one. We are just sure that one of these containments is non-trivial, and yet we cannot say which one it is. So it's an extremely tantalizing problem to clarify this complexity theoretic picture. And anyone who does that, anyone who shows that any of the containments that I have written in the first line there is non-trivial, would be doing a great service to complexity theory and would become a very famous computer scientist. Let's continue. What we can do is now we can picture these complexity classes as it's shown to you. As you can see, there's the class P, which is the smallest class. We suspect that NP is a slightly larger class. Then there's the class P space, which contains both these classes, and by Savage's theorem, it's also equal to NP space, and that is all contained in exponential time. Well, now what we want to do is look at our study of time complexity and recall NP completeness. NP completeness was a rich theory there. It was a very exciting theory which allowed us to identify hard problems, which allowed us to actually, in some sense, prove that these problems were NP complete, which was huge evidence that these problems may not be solvable in polynomial time. So we have now defined this class called P space. Well, the question is, are there any complete problems in P space? That's the question that we want to look at. Now what we want to do is we want to define P space complete problems. Let's start with a precise definition first. We will say that a language is P space complete if the first condition is, so we are looking at a language B and we will call it P space complete if B is itself in P space. And the second thing is that every language A in P space is polynomial time reducible to B. So if a language itself happens to be in P space and all the languages in P space are polynomial time reducible to that language, then we'll call it P space complete. Once again, if a language has the property that all the languages in P space are reducible to it, we'll simply call it P space hard. So if a language has both these properties, we'll call it P space complete. This definition is almost exactly a ditto copy of the definition of NP completeness, except for instead of the class NP, now we're using the class P space. So this picture shows you how a P space complete language will look like. It itself will live in P space and everything in P space will be reducible to it. So in some sense, it will be the hardest language in P space. Remember, that all the languages in P space will be polynomial time reducible to it. So here comes an extremely interesting and important question. The question is, why is it that we require that A is polynomial time reducible to B? Why don't we require that A is polynomial space reducible to B? So this is a very interesting question. It says, well, since we are studying space complexity, why don't we use the notion of space when we reduce languages? Why are we still using the notion of time? Well, the answer to this question is, if we go back to our theory of NP completeness, remember we there also use the notion of polynomial time reducibility. And what kind of reducibility was it? It was a deterministic polynomial time reducibility. Although we were studying the class NP, our reducibilities were deterministic polynomial time. They were not non-deterministic polynomial time. And the reason is, what we want to do is, we want the reductions to be easy. If the reductions are as hard as the class that we are studying, then this whole theory would become meaningless. So therefore, in the definition of P-space completeness, we also want the languages, all languages in P-space to be polynomial time reducible to our language, which we are trying to prove to be P-space complete. Well, what we want to say is that a P-space complete language is easy, then all languages in P-space are easy. In other words, what we want to do is, we want to prove the following theorem. So we want to define P-space completeness such that the theorem that I'm about to tell you is true. If this theorem is not true, then our whole theory of completeness will fall apart. Let's look at what this theorem says. This theorem says that if a P-space complete language is in P, then P-space is equal to P. Well, so in some sense, it's saying that if you want to prove that P-space is equal to P, then all you have to do is take one P-space complete problem and give a polynomial time algorithm for it. Well, because of this theorem, we start wondering if P-space complete languages are very hard. This theorem gives us evidence, once again not proof, that P-space complete languages are hard. And of course, this theorem tells us that P-space complete languages are the hardest languages in the class P-space. And if this theorem is not true, then there would be nothing interesting about these complete languages. Now let's go through the proof of this theorem and see where does polynomial time reducibility come when we go through the proof of this. The proof of this theorem reveals the answer to our question. Let B be any P-space complete language. So now what we're doing is we're proving this theorem. So I'm going to give you a proof of this theorem, and you would see that why polynomial time reducibility was needed to prove this theorem, and polynomial space reducibility would not have allowed us to prove this theorem. So let's go through the proof of this theorem. Let B be a P-space complete language. Let's say that B is in P. Then there is a polynomial time Turing machine that accepts B in time order n to the k. Now let us take any language A in P-space. Since A is polynomial time reducible to B, there is a polynomial time reduction f from A to B. So since A is polynomial time reducible to B, there is a function which maps sigma star to sigma star, which is computable in polynomial, and x is in A if and only if f of x is in B. That's just the definition of polynomial time reducible. And in this case, the function f is polynomial time computable. Now, let's consider the following algorithm. So now I will present an algorithm to you, which is going to be an algorithm or a Turing machine that accepts the language A. Let's look at this algorithm. So this algorithm takes as input some string x, then using n, it computes y equals f of x. Now it runs m on y, and if m accepts, then it accepts, and if m rejects, it rejects. This algorithm clearly recognizes the language A, and A was an arbitrary language in P space. And why does it recognize the language A? That's a simple consequence that f is a polynomial time reducibility. Let's see how much time does this algorithm take. The running time of this algorithm is order x to the k plus order y to the r, where n to the k was the running time of the first algorithm and n to the r was the running time of m. So this takes this much time. Now if the length of x is n, then the length of y is going to be less than or equal to n to the k. Thus the whole above algorithm that is given above will run in time order n to the kr, and this is polynomial time. Therefore this shows that the language A is in P. So what we've been able to show is that if any P-space complete language is in P, then all languages in P-space are in P. And this gives us very strong evidence that P-space complete languages are not going to be in P. It doesn't give us a proof, but it gives us very strong evidence. It does show us that P-space complete languages are the best candidates to be languages which are in P-space but not in P. They are the best candidates because if any one of them ends up in P, then all of P-space will become equal to P. Now, if instead of polynomial time reducibility, let us say that I had used polynomial space reducibility, then what would happen is f would be polynomial space computable instead of polynomial time computable. So what kind of theorem would have I proved? Or if I would have followed this same recipe, what kind of a result would I get? The critical point is that f was, in the previous theorem, a polynomial time computable function. If f were polynomial space computable, we could only say that the above algorithm runs in polynomial space. Thus, we will end up proving the following uselessly trivial theorem. And this theorem will say that if any P-space complete language is in P, then P-space is equal to P-space. As you can see, the conclusion of this theorem is completely trivial. We know that P-space is equal to P-space. Therefore, it doesn't tell us about anything about the hypothesis. And therefore, this is a completely uselessly trivial theorem. Since we don't want to do that, we want the fact that a P-space complete language is in P, we want it to have consequences. Consequences which are so far-reaching that it gives us evidence that this language is not going to be in P. Therefore, we use the notion of polynomial time reducibility. Let us make one observation. Suppose that B is a P-space complete language, and suppose that A is an NP. Then since A is an NP and NP is a subclass of P-space, therefore this language A is automatically in P-space. Now A is therefore polynomial time reducible to B. Thus, every P-space complete language is going to be NP hard. So all P-space complete languages are NP hard. All the problems in NP can be reduced to P-space complete languages in polynomial time. But they have the additional property that not only languages in NP, but languages in a larger class, the whole class of P-space, are polynomial time reducible to these problems. So a P-space complete problem is definitely as hard as an NP hard problem. And perhaps, and this is what everybody suspects, they're even harder. Since a larger class, since what we believe that P-space is a larger class than NP, therefore a larger class of problems is reducible to P-space complete problems. So this was a parenthetical note. Every P-space complete language is NP hard. Now let's recall Cook-Levin theorem. I said that Cook-Levin theorem was a very central theorem, not just in complexity theory, but it's one of the most celebrated theorems in all of computer science. What did Cook-Levin theorem tell us? The Cook-Levin theorem said that satisfiability is NP-complete. It gave us a vast understanding of the class NP. It identified one concrete hard problem in NP. What we want to do is identify such problems in P space. So, before Cook-Levin theorem, or before we studied Cook-Levin theorem, the class NP was an extremely abstract class of problems for us. But after Cook-Levin theorem, we could define NP to be the set of all problems that are polynomial time reducible to SAT. So SAT was a quintessential candidate or quintessential problem in NP. It was the hardest problem in NP. So Cook-Levin theorem took us from the abstract to concrete. It identified one problem that in some sense represented the whole class of NP. And therefore, it gave us a very nice understanding of this class. What we want to do is something similar now. What we want to do is come up with one problem which would identify the class, or in some sense represent the class P space. We want to identify a P space complete problem. So we're looking for an analog of the Cook-Levin theorem for the class P space. Well, let's review what was satisfiability, because that will probably lead us to the problem that we are looking for. So let's recall what satisfiability was. What we want to do is then later consider its generalizations. But let's look at SAT. We're given a Boolean formula on n variables x1 up to xn, and the question is, does this Boolean formula have a satisfying assignment? So, in other words, we make a Boolean formula using Boolean connectives ands, ors, and nots. We make a Boolean formula on n variables, and then the satisfiability question is there a way to assign true and false values to these variables which makes this formula true? That was the satisfiability question. Now let's phrase this question in a slightly different way. Let's look at the following formula. Another way to phrase SAT is to say, if the formula, there exists x1, there exists x2, there exists x3, all the way up to there exists xn, phi of x1 up to xn. So what it's saying is, does there exist x1, does there exist x2, does there exist x3, all the way up to xn, does there exist values for these variables such that when we plug in these values, this formula becomes true. So this is an equivalent formulation, or this is satisfiability written in a different notation. Now, when we look at it this way, one particular generalization stares us in the face. Let's see what kind of generalization is it. We notice that in the previous formulation of satisfiability, we're only using one quantifier, there exists. Now remember, when we studied logic and we made sentences and all that, there were actually two quantifiers. One was there exists and the other was for all. These are two extremely important quantifiers that we use to make formulas in logic. Well, what if we allow these quantifiers? What kind of formulas can we make? Let's look at an example. Let's consider the formula phi, which says that for all x, there exists a y, x or y, and not of x or not of y. This formula, the way I've written it, is what we are going to call a fully quantified Boolean formula. A fully quantified Boolean formula is also called a sentence, and it is either true or false. So, what we can do is, using quantifiers there exists and for all, and Boolean variables and Boolean connectives, we can make these fully quantified Boolean formulas. These are formulas which will have no free variables. The underlying universe that we are looking at is a Boolean universe. Every variable can take the value 0 or 1, true or false. So, when we write down a sentence like this, you'd remember from logic when you write down a fully quantified formula, and in this case a fully quantified Boolean formula, that formula is either true or false, and therefore sometimes we call it a sentence. So the question now we want to ask is, well, what happens if I write down a fully quantified Boolean formulas? How hard it is to tell whether such a Boolean formula, fully quantified Boolean formula, is true or false. Let us define our problem now. The problem TQBF is going to be the set of all encodings of phi such that phi is a fully quantified Boolean formula and phi is true. So you can write down a fully quantified Boolean formula, and the computational question now is to be able to design algorithms which will tell us whether such a fully quantified Boolean formula is true or not. From now on, what we're going to do is just simply call these QBFs, quantified Boolean formulas. And TQBF here means for true quantified Boolean formulas. So the language, the formal language, is the set of all, or the encodings of all Boolean formulas, fully quantified Boolean formulas which are true. In other words, if somebody tells you to design an algorithm for TQBF, you'll have to write an algorithm that reads a fully quantified Boolean formula, analyzes it, and tells us whether it is true or not. Well, what kind of a problem is this? If you think about it, this problem is harder than satisfiability. The reason it is harder than satisfiability is because it's a generalization of satisfiability. Satisfiability questions are special cases of fully quantified Boolean formulas in which all the quantifiers that they exist. Whereas in QBF or TQBF, you're allowed to write any quantifier you want for all or there exists. So this problem is going to be harder than satisfiability. Now let us first notice one thing. The TQBF is in P space. Well, the first claim is that we can prove that there is a polynomial space algorithm that will solve this problem for us, that would recognize this language. So our claim is that there is a polynomial space algorithm that can analyze a Boolean formula, quantified Boolean formula, and tell you whether it is true or false. This algorithm is going to require polynomial space. However, I'm not saying that this algorithm will require polynomial time. The only thing I'm saying is it would require polynomial space. How would we design such an algorithm? Well, such an algorithm is almost obvious once we actually formally define what does it mean for a fully quantified Boolean formula to be true. If phi is a formula on 0 Boolean variables, then we can simply evaluate it to find out whether it is true or not. So suppose if I give you a Boolean formula which had no variables in it, so it had only constants, and the constants are 0 and 1, or the constants are true and false. So I give you a Boolean formula, I connect true and false using ands, ors and nots, and I want to ask you whether this thing is true or not. You can simply evaluate this formula by using the usual interpretation of and or. So it's very easy to tell if a Boolean formula or quantified Boolean formula on 0 variables is true or false, because it's simply constants 0 and 1 connected by ands, ors and nots. Let's look at an example. 0 or 0 and 1 or 0 is false, because if you give the usual interpretation to and or, then 0 or 0 is 0 and 1 or 0 is 1, but 0 and 1 is 0, therefore this evaluates to false. On the other hand, 1 or 0 and 1 or 1 is true. I'm just simply evaluating these formulas. So it's very easy for an algorithm to tell if a Boolean formula on 0 variables is true or not. It simply evaluates them, and you can simply write an algorithm to do that, and it would not take too much space. In this case, it would also not take too much time. Now, Suppose that you have a very complicated Boolean formula and it has quantifiers q1 with x1, q2 with x2, all the way up to qn with xn. So this is a formula on n variables, and each of the quantifiers is, of course, either for all or there exists. Then by looking at this formula, we can obtain two formulas. The first formula is obtained by substituting 0 for the variable x1, and the other formula is obtained by substituting 1 for the variable x1. So you take a formula which is on n variables, in which all the variables are quantified. You can take the first variable, and now you can throw away the first variable and obtain two different formulas. The first one is obtained by setting the first variable to be true, and the second formula is obtained by taking the first variable to be false. Let's look at an example. For example, suppose we have the formula that we already discussed. For all x, there exists y, x or y, and x bar or y bar. Now, from here, what we can do is we can obtain two formulas. So phi substituted with x equals 0 is there exists y, 0 or y, and 0 bar or y bar. The other formula, phi substituted with x equals 1, is there exists y, 1 or y, and 1 bar or y bar. As you can see, to obtain these two formulas, I have not done much. What I have done is remove the first variable from the quantified part, and wherever this variable appeared, in the first case I've put a 0 wherever this variable appeared, and in the second case I've put a 1 wherever this variable appears. So I can obtain these two formulas. Now let's continue with our definition. We define for all x1 phi to be true if both of these formulas are true. So this is an inductive definition. We assume that we have defined what does it mean for a formula to be true on n-1 variable, and I'm giving you the definition for n variables. So in this case, what we do is we remove the first variable, we substitute it as 0 in one case and substitute it as 1 in the second case. Now, the quantifier with the first variable was for all, and now we'll declare the large formula, the one from which we remove the variable, to be true if both of these formulas obtained turn out to be true. Similarly, what we will do is make a definition where the quantifier was a there exists or an existential quantifier. So we will define there exists x1 phi to be true if one of these formulas obtained by substituting 0 for this variable and the other obtained by substituting 1 for this variable, if any one of them turn out to be true, then we'll declare the original formula to be true. Thus, what I have given you is an inductive definition of what it means for a Boolean formula, quantified Boolean formula, to be true. Well, what you should do is now review this definition and think about it so you know when a Boolean formula, quantified Boolean formula, is true and when it is false. If you think about it, this is exactly the same definition that we had used when we were studying logic and Gödel's theorem and things like that. In this case, these definitions are much simpler because the universe that we are working with is the Boolean universe. So the variables can only take values 0s and 1s. This is just a specialization of the definition that we have already done. Once you understand what does it mean for a Boolean, quantified Boolean formula to be true, you'd see that the very definition throws an algorithm at your face, throws an algorithm at you. And what we'll do is we'll analyze this algorithm. In the next lecture, we will look at an example and see if a concrete Boolean formula is true and look at the algorithm that we obtain. Then we'll prove that this algorithm is a polynomial space algorithm, thereby showing that this formula, quantified Boolean formulas, is in polynomial space. I'll see you next time. Thank you and goodbye.